Welcome to Math with Professor V. This is video lecture for section 5.1 for business calculus on increasing and decreasing functions. So let's just do a quick recap of what it means for a function to be increasing or decreasing, and then we're going to get into the lesson and see how we're going to use our calculus to determine this information. So let f be some function that's defined on an interval. Then for any two numbers, x1 and x2 in the interval, we say that f is increasing on that interval if f of x1 is less than f of x2 whenever x1 is less than x2. Now don't let the math definition freak you out. It's not as bad as it sounds. I'm just going to give you a little 2D graph and hopefully that'll help clear things up. So I'm just going to put everything in the first quadrant. Whenever x1 is less than x2, so that means x1's here, x2's bigger, somewhere over there. Remember, f of x1 refers to the function value, the y value at x1, and f of x2 is the y value at x2. So the function value, the y value, is smaller or lower at f of x1 compared to f of x2. So say here's f of x1, f of x2 needs to be higher. And this is our function. I have no other info besides the fact that this y value at f of x2 is bigger. Well, yeah, clearly you could see what's going on this interval. The function's increasing. Straightforward. Similarly, we say that a function is decreasing on an interval if f of x1 is greater than f of x2 whenever x1 is less than x2. So similar picture, x1 is still less than x2, but notice the direction of the inequality is different now for the function values, for the y values. So here's x1, here's x2. F of x1 is bigger though. So f of x1 is going to be here, f of x2 is smaller, and yes, hopefully you can clearly see the function is decreasing. When we talk about increasing, decreasing, we're always looking left to right in the x direction. Okay, so you just imagine you're walking on the graph, always to the right, you're going downhill, that means decreasing. All right. We say that a function is constant on the interval if f of x1 equals f of x2 for all x1 and x2 in the interval. So hopefully that's straightforward. You have a horizontal line or it's flat on the interval from x1 to x2 if all the function values, all the y values are the same. Okay, now hopefully you've had a little bit of experience listing intervals of increase and decrease, but if not, let's just do a little review example right now. Given the following graph of h of x, list the intervals where the function is increasing and decreasing. Okay. Now, when you're listing intervals of increase and decrease, you only list the x values. In fact, that's so important. I'm going to write it down here. Only list the x values. The word increasing already tells you that the y values are going up. The word decreasing already tells you the y values are going down. You're just interested in locating where relative to the x-axis that's happening. So we only give the x values. So where is the function increasing? Well, when are you, if you're walking on it from left to right, going uphill? So it looks like downhill, 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 downhill. Whoop, something's happening right here. All of a sudden, we're going uphill. We are going uphill, 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 and then stops here. And then the rest of the way is downhill. So the function is increasing from this piece to this piece. Now you have to give it in terms of x values. So this is from, looks like x equals 1 up until x equals 5. And I'm going to list this as an open interval from 1 to 5. That's x equals. It's not an ordered pair. It's an interval. Okay. These we always list open. It depends on the textbook. It can get to be quite a contentious topic amongst some math instructors. But anyways, for the sake of this course, we write them with open intervals anytime we do intervals of increase, decrease with our critical numbers moving forward. Okay, as far as decreasing, when are we going downhill while walking on the graph? All right, from here on, right, we said well, when did we start going downhill? Well, all the way from negative infinity, right? We were going downhill this whole time. And then we're still going downhill on this little separate piece here. So I'm going to have to list two intervals together. We're decreasing from negative infinity to 1, union, this point right here, the x value was 5, and then we're decreasing forever on out from there. Okay, and again, these are open intervals. Okay, perfect. How are you guys doing? Good? Okay, now let's get into how calculus comes into play. Critical numbers. The critical numbers for a function are those numbers C in the domain of f, that's important, we'll talk about that in just a hot second, for which f prime of c equals 0, or f prime of c does not exist. So these are the two conditions in which we obtain critical numbers. A critical point is a point whose x-coordinate is the critical number c and whose y-coordinate is f of c. So you'll hear the word critical number, that means just the x value, c, and then the critical point is an actual ordered pair, it's a point, x comma y. All right, so what we're going to do now is use the first derivative test to determine where a function is increasing and decreasing. Suppose a function f has a derivative at each point on an open interval. Then, if f prime of x is greater than 0, if it's positive for each x in the interval, f is increasing on the interval. If f prime of x is less than 0 for each x in the interval, f is decreasing on the interval. And if f prime of x equals 0 for each x in the interval, then f is constant on the interval. And I don't want you to just memorize this. I want you to understand why this is the case. And I'm just going to draw you a quick little graph. And the more it makes sense, then you won't just blindly be memorizing stuff, okay? So here's a function. Boom. Look at that. Here's a few places of interest. Okay. Notice, we could say, yep, for sure, the function is decreasing on this interval right here, up until whatever value this is. I'll call this A, I'll call this B. The function's decreasing from negative infinity to A. Decreasing means the derivative is negative there. Does that make any sense? Well, we know f prime of x gives us the slope of the tangent line to the curve at a given point. And if I were to draw a bunch of little baby tangent lines to this curve, notice they're all sloping downward. They have negative slopes. You see that? And then once we come to A, boom, horizontal line, horizontal tangent. That means f prime of A is equal to 0. So A is a critical number. Yes, it is. Okay. Look at B. From here on out, the slopes are changing. Now the slopes are positive, positive, positive. That means the derivative is positive and the function is increasing. And then boom, you draw a tangent line here, horizontal tangent. That means f prime of b is equal to 0. B is also a critical number. And then from here on out, these tangents all have negative slopes. And again, the function is decreasing on that interval. So that's how we use the derivative to give us information about whether or not a function is increasing or decreasing. And those critical numbers are key in showing us where that change may or may not occur from increasing to decreasing. Okay, so let's get into some examples. It'll all come together. Another important thing to remember is critical numbers have to be in the domain of the function. So what I recommend doing anytime you start a problem where you're asked to find critical numbers and intervals of increase and decrease, list the domain of the function first before you get into the problem so you don't forget about this fact. Okay? All right, I know it's a lot of information. Let's just jump right into it, and then once you get the hang of it, it won't seem so daunting. Okay, examples. For each function, find part A, the critical numbers, and then B, the open intervals where the function is increasing, and then C, the open intervals where it is decreasing. So they're being specific that they want these intervals to be open, where it's increasing and decreasing. So make sure you put parentheses on all the intervals, no brackets, okay? All right, let's look at f of x. It's 4x cubed minus 9x squared minus 30x plus 6. Well, that's a polynomial. And I know polynomials, their domain is all real numbers. So we don't have to worry about having any restrictions in the domain and having issues while finding critical numbers. So that's good. So to find critical numbers, we have to figure out where the derivative f prime of x equals 0 and where it doesn't exist. So first things first, let's take a derivative. F prime of x is going to be 12x squared minus 18x minus 30. Okay, so there's two conditions where we find critical numbers, where f prime of x is equal to 0 or where f prime of x does not exist. Now, since this is a polynomial, there aren't going to be any places where it doesn't exist. It's defined for all real numbers, so this is none. But f prime of x equaling 0, let me set the derivative equal to 0. And I'm not going to try to factor just yet. I'm noticing I can divide everybody by 6 on both sides. You could factor it out, but I'd rather just be done with the 6, you know? I don't even want to look at it. 2x squared minus 3x minus 5 is 0. And then factor 2x minus 5 and x plus 1, yes? Beautiful. So from here we get that x equals 5 halves or x equals -1. So those are our critical numbers. Some textbooks call it critical values. If I say that by accident, excuse me, but they're the same thing. Critical numbers, critical values. Just depends on the text. Okay. Part A is done. Now we need to find the open intervals where the function's increasing and where it's decreasing. So what we're going to do now is make a number line to test the signs of the intervals that get broken up according to the critical numbers. So we're going to make a number line. Boop, boop, boop. Label it f prime of x. This is the first derivative test. Put the critical numbers on the number line. You need not stress about it being scaled or having a bajillion tick marks. All you do is you go, oop, my critical numbers are 5 halves and -1. -1 is smaller, and I'm just going to put them equally spaced out. You live your life. This is just for testing purposes. So what we do is we check now a representative value in each of these 3 intervals that we've broken up the real number line into to see whether or not the derivative is positive or negative there. So pick somebody as a representative value on the interval from -infinity to -1 and don't actually pick the critical number. We want to check if the derivative is positive or negative there. And if I plug in any of these numbers, they're the critical numbers. They're just going to give me 0. It won't tell me if it's positive or negative. So pick something smaller than -1. I'm going to go with x equals -2. And actually the best place to figure out whether or not the derivative is positive or negative here is not the original version, but right down here where you factored. Because watch this. -2. 2 times -2 minus 5, that's negative. And then -2 plus 1, that's also negative. So I have a negative times a negative. And I'm not really interested in what the value of the derivative is. I just want to know whether overall it's positive or negative. So on the interval from -infinity to -1, it's positive, right? And you could try a different number just to be sure, but usually 1 is more than enough. You could put -10, -1,000,000, whatever your heart desires. This is negative, overall it's positive. What does that tell me about my function f of x? It means f of x is increasing on that interval, okay? So right up above, I'm going to draw an arrow sloping upwards to remind me that my function f of x is increasing there. Okay, now we have to move on to the next interval. So pick somebody between -1 and 5 halves to test into these two factors to see if the derivative is positive or negative. You know what's a great number? 0, yes, I love it. Okay, So this is going to be 0 minus 5, that's negative. 0 plus 1 is positive. So that means the derivative is negative on this interval. So the function is decreasing. Very good. Well done. Last interval from 5/2 to infinity. Remember, 5/2 is 2.5. Something bigger than that, we could do x equals 3. And then now let's test. So 2 times 3, that's 6 minus 5. This is positive, this is positive. So the function's increasing there. Positive, positive, derivative's positive, f is increasing. So I'm going to just answer parts B and C all together. So B wants where the function's increasing. That's from negative infinity to negative 1. And then you put union from 5/2 to infinity. And then part C wants decreasing. And that's only from negative 1 to 5/2. Good? Okay. Let's move on. Let's take the spice level up a notch. And here we have a rational function, f of x, which equals x plus 3 over x minus 4. Now, for rational functions, remember, we always have to pay attention to the denominators and make sure the denominator is never 0. And x minus 4, that would be 0 if x is 4. So my domain is all x's such that x can't equal 4. Don't forget to write that out first, okay? Good. So now let's try to find our critical numbers. First thing I need to do is take the derivative. So we need to find f prime of x. And we're going to use the quotient rule. So here we go. Low means denominator. D high, derivative of the numerator, minus high, numerator. D low, derivative of the denominator, over x minus 4 squared. And then let's clean up. This is x minus 4 minus x minus 3 over x minus 4 squared. And then do you see how these x's cancel? Oh, good. Okay, so I just am left with negative 7 over x minus 4 squared. Okay, I'm going to teach you a really important shortcut that's going to help you. If your derivative is in the form of a fraction, a rational function, then when the numerator is 0, that means f prime equals 0. If the denominator equals 0, that means f prime does not exist. Because when you go to find the zeros of a function, if you set the whole thing equal to 0, then the very next step is you always clear out the denominator, so it disappears from the equation, and you end up just solving wherever the numerator is 0. So you can bypass those first introductory steps. And since a lot of the time these are the two things that we're interested in, it's helpful just to jump straight to the crux of the problem. Okay? So here we go. Let's get our critical numbers. Tell the people what we're doing. We're finding critical numbers. So f prime of x equals 0. That would mean the numerator, negative 7, is 0. Well, that's impossible. None. And then the other place where we can get critical numbers is where f prime of x does not exist. So that would mean the denominator, x minus 4 squared, is 0, which would mean x has to equal 4. But that is not in the domain. Remember, I had us write the domain out earlier. The domain is everything except 4. So, nope, that's not a critical number. Oh no, it's okay. We didn't do anything wrong. No critical numbers. Now, we still need to answer where the function is increasing and decreasing. And you can tell right now that this derivative is always negative. You see how the denominator is squared? That means it's always positive. And we have a negative constant in the numerator. So the function is always going to be decreasing on its domain. It's increasing nowhere. Increasing nowhere. Decreasing, and then here's where you have to be careful. You're not going to say from negative infinity to infinity, because remember, x equals 4 is a domain restriction. So you have to jump over it. So you would say it's decreasing from negative infinity to 4 union 4 to infinity. And I just forgot which part was A and which, decreasing is part C. Okay, perfect. Now, you can still make a number line for this situation. If you're like, I would not have noticed that it's always negative. No problem. You make a little number line, call it f prime. Since we have this domain restriction at x equals 4, remember back to when we were studying rational functions, that means there's a vertical asymptote at x equals 4, yes? So you're going to add that on. That's important. And then you check the sign of f prime on either side of that vertical asymptote. So something smaller than 4, I mean, like I said, it doesn't matter. You can plug in whatever, 0, a million, just not 4. The derivative's always coming out negative, which means the function's always decreasing on its domain. So you can see here's this interval negative infinity to 4. And then 4 to infinity. So don't write negative infinity to infinity, that's wrong. We got it? Okay. You have to be always mildly paranoid in math that there's some minor detail that you've overlooked, so you don't make careless mistakes. Okay, next one, y equals negative square root of 9 plus x squared. So first let's think about the domain. I know when I have a radical function with an even index, like square root, fourth root, sixth root, I have to make sure what's underneath is not negative. But you know what? We're squaring x and then adding 9. For sure, this is always positive, right? If you square something, it's positive, and then I'm even adding to it. So we're good. We have no restrictions. I'm just going to write down that the domain's all real numbers so that we know we can rest at ease. And then before we go ahead, let me rewrite the function so we can take the derivative more easily. I'm going to call it f of x instead of y, just because I like it better, equals negative 9 plus x squared to the 1/2 power, okay? And then now when we take the derivative, I'm going to use my power rule and the chain rule at the same time. So f prime of x equals, that negative just comes along for the ride. Move the 1/2 down front, leave these parentheses alone. Don't forget to subtract 1. The new exponent's going to be negative 1/2. Inside goes exactly what we had before. Don't touch a thing. And then by the chain rule, now I multiply by the derivative of the inside, which is 2x. We got it? Oh, good. Okay. Then, hooray, this 2 and 1/2 cancel. And then I'm just left with negative x over, you bet, I'm going to put square root 9 plus x squared in the denominator. There's my f prime. Okay, so critical numbers come from 2 places, but you're going to do the little shortcut I showed you, right? So we know f prime equals 0 happens when just the numerator is 0. So that means negative x equals 0. That happens if x is 0. Great. Critical numbers also come from when f prime does not exist. That happens when the denominator is 0. That's never going to happen though, right? That would mean 9 plus x squared is 0. X squared is negative 9. That doesn't have any real solutions. So none from this case. So my only critical number is x equals 0. That's the answer to part A. Okay, now let's figure out where the function is increasing, where it's decreasing. So we're going to make our number line. We put our one and only critical number on there, 0, 0 the hero. And then let's test. So pick a number smaller than 0. How about negative 1? Do you like that? Good. So if I pick negative 1 in for x, negative 1 is positive. And then this denominator is always positive because you have a positive number under here. You take the radical, it's still going to be positive. So positive divided by positive is positive. My function is increasing. Pick something bigger than 0. How about 1? Negative 1, so the numerator is negative. Denominator is always positive. Negative divided by a positive, negative, decreasing. So then we can say, let me write the answer up here. The function is increasing from negative infinity to 0, and then decreasing, good, from 0 to infinity. Perfect. Okay, how was that one? Good. I just got a couple more. Example D. F of x equals ln of 5x squared plus 4 over x squared plus 1. Now again, let's think about the domain. For natural log, I can't have any negative values. The argument can't come out to be negative, nor can it be 0. It has to be positive. That's a better way of saying that. Okay, so I'm looking here. There's no way this is going to be 0. It's always positive. There's no way this is going to be 0 either. Everything's always positive. So I have no restrictions. Oh, that makes life easy. So the domain is all real numbers. Now, I wouldn't just go ahead and take the derivative just yet, because then otherwise when you do the chain rule, you're going to have to do nasty, nasty quotient rule. I mean, the quotient rule is not the end of the world, but if we can avoid it, let's avoid it, you know? Especially because we have this beautiful natural log, and I can use my properties to rewrite it as ln of 5x squared plus 4 minus ln x squared plus 1. So if you'll recall, ln of a divided by b equals ln of a minus ln of b. Okay, now it's going to be much easier to take the derivative because the chain rule is going to be a shorter process. No quotient rule necessary. So f prime of x is going to be, remember, derivative of ln something is 1 over the something, and then by the chain rule, I have to multiply by the derivative of the something. So I'm just going to jump straight to that. The derivative of 5x squared plus 4 is 10x, and just put that in the numerator right away. Similarly, you could do the same thing on the next one. So put x squared plus 1 in the bottom, and then you know you're going to do the chain rule right now, so then just put 2x in the top. Nice, right? Okay, to figure out where the derivative is 0 and where it doesn't exist, I need it to be one term. So I need to get a common denominator. So I'm going to multiply this first one by x squared plus 1, top and bottom. And then the second one, do you need me to write that out? Maybe, huh? The second one's going to get multiplied by 5x squared plus 4. Okay, good. So then I have minus 2x times 5x squared plus 4 over 5x squared plus 4 times x squared plus 1. Okay, remember, 99% of the time in your math career, you're not multiplying out the denominator. You leave it alone. We're going to just distribute in the numerator and clean things up. So this is going to be 10x cubed, right? Plus 10x minus 10x cubed minus 8x over 5x to, no, what am I writing? 5x squared plus 4 and x squared plus 1. Okay, so 10x cubed is gone, and then I can combine like terms. So 10x minus 8x, at long last I can say f prime of x is 2x over, I need this a little longer, 5x squared plus 4 times x squared plus 1. Beautiful. Okay, so let's get our critical numbers. They come from two places where f prime of x equals 0 and where f prime of x does not exist. So f prime of x equals 0, that happens when the numerator is 0. So that means 2x equals 0. That's when x is 0. Great. F prime doesn't exist when the denominator is 0. That means either 5x squared plus 4 is 0 or x squared plus 1 is 0. But remember, these don't have real solutions. 5x squared equals negative 4. That's not possible. We have no real solutions to that equation, only imaginary, and we're not working in the complex plane in this class, so don't worry. So none from that case. So our answer for part A is just x equals 0. Okay, good. And then we have to determine where the function is increasing and decreasing. So let's make our number line, label it f prime, always label it, and then put our one and only little critical number there. Okay, so pick a number smaller than 0. How about -1? 2 times -1 is negative, so numerator is negative. And then this denominator, remember it's always positive. You square something, you add a number, that's positive, that's positive. So we have a negative divided by a positive, that's negative. So the function is decreasing on that interval. And then something bigger than 0, say we plug in x equals 1, positive, positive. Everyone's so positive, I love it. Positive, boom. Okay, so let's list out then the intervals. The function's increasing where? Just give the x values, 0 to infinity, and then it's decreasing from -infinity to 0. Beautiful. I have one bonus problem. I think you guys should try it on your own, because then you'll really know if you have the lesson under control. It's like when you watch something, that's just the beginning of starting to understand a process. The real truth of it unfurls when you try to do it on your own. Okay, so here's the function, same directions. Find the critical numbers, find where it's increasing and decreasing. I think you should pause the video, give it a try on your own, and then check back in right now. Okay, did you list the domain first? Very good, it's all real numbers, that's nice. Now the derivative, f prime of x, it's gonna be 4x cubed plus 12x squared plus 8x plus 0. Beautiful. So critical numbers come from two places where the derivative equals 0. So where f prime of x equals 0 and where f prime of x does not exist. Now, since this is a polynomial, right, there's no denominator and the domain is all real numbers. So there's not going to be any critical numbers from where the derivative doesn't exist. But I will go ahead, let's see where it's equal to 0. So let's set 4x cubed plus 12x squared plus 8x equal to 0. And then I want to divide out, or you know what, let's just factor out the GCF. I can take a 4x out from everybody, right? You can divide through by 4. You can divide through by a non-zero constant, but you can't divide both sides of an equation by a variable ever, okay? So don't even think about it. The math police will come snatch you quick, fast, and in a hurry. So just to play it safe, if you always want to just factor out the GCF, you can do that. This will be x squared plus 3x plus 2. Very good. And it factors like a dream. X plus 2, x plus 1 equals 0. So set each of the factors equal to 0. The lonely little 4x means x equals 0 is a solution, or also a critical number. So is x equals -2 and x equals -1. So this is the answer to part A. We've got 3 critical numbers. Look at us. Did you get them? You did? Oh, good. If you didn't, it's okay. Try it again later. Hopefully you learned something. Now let's find where the function's increasing and decreasing. Let me not call it B yet. And let me put all my critical numbers on there. So we've got -2, -1, 0. So this time, do you see how many intervals we have to test? 1, 2, 3, 4. Holy smokes, we can do it. Okay, pick a number smaller than -2. How about -3? Where am I plugging it in? Not here. No way. Come here where it's factored. Yes. Negative, negative, positive. That's negative. The function's decreasing. Pick somebody between -2 and -1. How about -1.5? Negative, positive, negative. Negative, positive, negative is positive. The function is increasing. Okay, what about between -1 and 0? How about x equals -1/2? All right. Negative, positive, positive. That's negative. And then bigger than 0, how about 42? Positive, positive, positive. You could pick 1 also. I just felt like spicing it up. Okay, I know what you're thinking. I know. Does it always alternate like this? No. Sometimes it'll be negative back to back, like 2 decreasing or 2 increasing. Remember we saw that earlier. Let me remind you. Right here. They were decreasing, decreasing. So no, you can't take it for granted that it's always going to switch. That's not true. That's not true. You got to test them all, okay? If there was a shortcut, I would tell you, please. I'm not a gatekeeper of a professor. So please know if there's like a better way, a cleaner way, a tip, I'm always sharing that info with you guys. Okay, so here we go. Let's list out where the function is increasing first. So increasing from -2 to -1, union 0 to infinity, and then decreasing from -infinity to -2, union -1 to 0. Boom, we are done. That was nice. Hope you enjoyed the video. Don't forget to subscribe, give it a thumbs up, leave me a comment down below. Let me know what math class you're taking right now. Are you in business calc or are you just watching for personal enrichment? I have all sorts of people watching for different reasons on my channel, so I'm always curious about everyone's math journey. Thank you guys so much for your support. And you can also follow me on Instagram, TikTok, Math with Professor V. Shop my merch if you want some Math Police sweatshirts and caps and whatnot. One of my former students designed the logo, actually. And I will be back sooner than later. Bye.